Imagine walking into a smart factory where machines are constantly communicating, sensors detect minute changes, and alerts are triggered automatically. But the system never misses a beat. Behind this seamless operation is a structured IoT architecture that ensures data flows efficiently from sensors to actionable insights. In this lesson, we'll explore the 4 layers of IoT: device, connectivity, data, and application, and how each component interacts to create reliable, real-world systems. You'll learn not just the theory, but how to reason about sensor selection, network choice, processing location, and application design. By the end, you'll understand how to architect IoT solutions that are scalable, responsive, and practical, skills you can immediately apply to your ESP32-based projects. The device layer is where your IoT system touches the real world. Sensors capture physical data, temperature, humidity, motion, while actuators perform actions like switching a relay or adjusting a fan. When I first built a greenhouse monitoring system, I learned that choosing the right sensor and correctly calibrating it saved days of debugging. Microcontrollers like ESP32 act as the bridge, collecting data, performing local decisions, and forwarding information to higher layers. Always ask yourself, how accurate does this sensor need to be? How fast should the actuator respond? Understanding these constraints ensures your system behaves predictably under real-world conditions. Connectivity is the nervous system of IoT. It carries data from devices to processing systems. Protocols like Wi-Fi, BLE, LoRa, or MQTT each have strengths. Wi-Fi is fast and familiar, BLE is low power for local communication, LoRa handles long range with minimal energy, and MQTT is lightweight for cloud messaging. When I deployed a multi-sensor ESP32 network in an industrial setup, poor protocol choice led to packet loss and delays, teaching me that connectivity decisions affect reliability as much as sensor quality. Consider range, power, and data volume before selecting a protocol, and remember, a system is only as fast and reliable as its network. The data layer is where raw sensor readings turn into actionable insights. This can happen locally on the ESP32 or remotely in the cloud. Local processing reduces latency, critical for instant responses, while cloud storage enables historical analysis, dashboards, and predictive models. In a vibration monitoring project I worked on, preprocessing data locally filtered noise before sending it to the cloud, saving bandwidth and improving decision accuracy. Think carefully about where computation should occur, what data to store, and how to structure it for reliability and scalability. Clear data flow design here simplifies debugging and makes your IoT systems robust. The application layer is the interface between humans, systems, and IoT devices. It can be dashboards, mobile apps, alerting systems, or automated triggers. In a smart irrigation system I built, the ESP32 collected soil moisture data, processed it locally, and pushed only relevant updates to a dashboard for remote monitoring. Here, the application defines how data is interpreted and actions are presented. Ask yourself, what decisions are automated versus monitored? A well-designed application layer provides clarity, control, and timely interventions, completing the chain from sensor to action. In this lesson, you explored the 4-layer IoT architecture: device, connectivity, data, and application, and learned how each layer interacts to turn sensor readings into actionable decisions. By examining real-world examples and reflecting on design choices, you now understand how to select devices, choose communication protocols, structure data, and design applications for ESP32-based IoT systems. These insights give you a foundation to architect reliable, scalable, and practical projects, whether you're prototyping a home automation system or deploying an industrial sensor network.